Welcome to the deep dive. Today we're tackling something pretty fundamental, the physics of electricity in our own atmosphere. We're pulling our insights mainly from Chapter 9 of the Feynman Lectures on Physics, Vol.2, a real classic. And let's just kick things off with something that sounds, well, frankly unbelievable. If you're standing outside on flat ground right now, your head is about 200 volts higher in electrical potential than your feet. You're basically walking through a constant electric field.
Yeah, that's usually the first thing that makes people go, wait, what? If there's 200 volts across my body, why don't I feel a shock? Why can't I, plug my phone into my hat? And that's really our mission for this deep dive. Figure out why that is. We need to understand this natural electrical state of the air, what keeps the Earth charged up, and how it all connects to something as dramatic as lightning. It's this puzzle.
Yeah.
Why doesn't the Earth's charge just leak away?
Right. So let's start with that field itself. You said 200 volts head to toe. That comes from a general field near the surface of about, what, 100 volts per meter?
That's the typical value, yeah. 100 volts for every meter you go up.
So walking up a single flight of stairs,
Yeah.
maybe 3 meters, you've just increased your potential by 300 volts compared to the ground floor.
Exactly. Sounds pretty dangerous when you put it like that. But this is where we hit that safety paradox, and the explanation is actually quite straightforward.
It comes down to conductivity, doesn't it?
Precisely. Your body, it's a really good conductor. And the ground, well, for electrical purposes, we treat it as an equipotential surface. Basically, it's all at the same voltage. Let's call it zero. So when you're standing on the ground, you're connected to that zero potential. Your whole conductive body equalizes to that same ground potential. The electric field lines have to bend around you.
Ah, okay. So the voltage difference exists in the air, but not across me because I'm connected to the ground.
Right. And the crucial part is the air itself. Air is a terrible conductor. It has incredibly high resistance. So even though there's that 100 volts per meter potential difference available in the air, almost no current can actually flow through it or through you because the resistance is just too high. High voltage, but vanishingly small current. That's why you're safe.
Okay, that makes sense. Voltage isn't dangerous on its own. Current is. And the air blocks the current. So how do scientists even measure this field if it's so subtle in its effect on us?
Feynman mentions a few methods. One classic way involves using an insulated conductor, like a metal plate sitting on, say, insulating posts just above the ground. Initially, it might collect some charge from the air. If you briefly connect it to the ground with a wire, that charge flows away, and the plate is at 0 volts.
Okay.
Then you disconnect the wire. Now, the electric field in the air starts pulling charge back onto that insulated plate. By measuring how much charge accumulates over time, or the potential it reaches, you can calculate the strength of the field pushing that charge. It's clever.
Very clever. So the air is a poor conductor, but not a perfect one. You said charge can move onto that plate. Does that mean there's actually some current flowing through the air all the time?
Yes, exactly. And this is where it gets really interesting. There is a constant, albeit very small, current flowing vertically downwards from the atmosphere to the negatively charged Earth.
What makes the air conductive at all then, if it's such a poor conductor?
It's ionization. Air molecules, mostly nitrogen and oxygen, are neutral, but they're constantly getting knocked apart into positive and negative ions. There are two main culprits doing this knocking. One is natural radioactivity from rocks and soil in the ground. The other, and it becomes more important higher up, is cosmic rays, high-energy particles zipping in from outer space.
Ah, cosmic rays. I remember hearing about Hess discovering those with balloons, measuring more ionization the higher he went.
That's the one. So you've got this constant production of ions. The electric field then pushes the positive ions downwards toward the negative Earth and pulls the negative ions upwards. This movement of charge is an electric current.
Okay, a tiny current. How tiny are we talking?
The current density is minuscule, about 10 microamperes. That's 10 millionths of an amp flowing down through each square meter of air. Seems like nothing, right?
Sounds incredibly small, yeah.
But now you have to think globally. You have to add up that tiny current over every single square meter of the Earth's entire surface.
Okay, the surface area of the Earth is huge. So this tiny current per square meter must add up to something significant. This is the so what moment, isn't it?
It really is. When you do the math, integrating that 10 microamps per square meter over the whole globe, it comes out to roughly 1,800 amperes.
1,800 amps. Just
Yeah.
constantly flowing down onto the Earth from the air.
Yep, 1,800 amps. That's a serious amount of current, like what might power a small factory constantly discharging the Earth.
And the Earth is negatively charged. So this downward flow of positive charge is constantly neutralizing that negative charge.
Exactly. And here's the big puzzle Feynman highlights. If you just had this discharge current and nothing else, it would neutralize the Earth's total negative charge completely in about half an hour. Poof! No more atmospheric electric field.
But the field is still here. It's
None.
constant. We measure it every day.
Right, which means there must be some other process, some giant natural mechanism that's constantly pumping negative charge back onto the Earth's surface, fighting against that 1800 amp leakage current.
It maintains this huge potential difference. You mentioned up to 400,000 volts between the ground and the upper atmosphere, maybe 50 kilometers up.
Yes. So the Earth acts like a giant leaky capacitor, constantly losing charge, and something has to be acting like a battery, constantly recharging it.
Okay, so what is this giant atmospheric battery?
Thunderstorms. That's the answer. Thunderstorms are the engines, the large-scale batteries that do the job. They somehow separate charge and effectively pump negative charge back down to the Earth.
And there are lots of them happening all the time.
All the time. On average, there's something like 300 thunderstorms active around the world at any given moment. They collectively act as the charging mechanism for the entire planet's electrical system.
Wow. 300 global recharging stations operating continuously. That's amazing. You mentioned something about synchronization, too. It's not just random local weather.
Yeah, this is a fascinating detail. If you measure the overall atmospheric electrical activity globally, it peaks around 7 p.m. Greenwich Mean Time. Every day.
7 p.m. GMT. Not local afternoon or something. Why GMT?
It's because most of the Earth's big land masses, where thunderstorms form most intensely due to heating, are concentrated more on one side of the globe than the other. Think Africa, the Americas. When it's late afternoon and prime thunderstorm time over those large land areas, that corresponds to about 7 p.m. GMT. So the peak electrical activity of the whole planet is synchronized to that time, driven by where the continents are.
A global electrical heartbeat timed by geography. Okay, let's get inside one of these storms. How does a single thunderstorm cell manage this incredible feat of charge separation? What's the structure?
Well, you need to picture the dynamics. It starts with warm, moist air rising rapidly. That's the updraft. As it goes higher, it expands and cools down.
Adiabatically, right? Cooling just from expansion, not by losing heat.
Exactly, adiabatic cooling. This causes the moisture to condense into water droplets and higher up freeze into ice crystals, forming the massive cloud. In a mature storm, you have this powerful updraft carrying moisture and ice way up, sometimes 20 kilometers high. And alongside it, you get downdrafts, bringing cooler air and precipitation back down. It's a hugely energetic convection cycle.
A chaotic mix of rising and falling air, water, and ice.
Yeah.
And somewhere in that chaos, the charges get separated.
Yes, that's the key. Somehow this process consistently leads to positive charge accumulating near the top of the cloud and a large concentration of negative charge near the bottom.
Creating this massive electrical dipole in the sky. What's the mechanism physically separating positive from negative?
There have been a few theories, like involving breaking water drops, but the one Feynman discusses, Wilson's mechanism, is really elegant because it uses the existing atmospheric field we started with.
The 100 female field plays a role inside the storm, too.
Wilson proposed it does. Think about a larger falling water drop or an ice crystal inside the cloud. Because it's conductive, that weak ambient field induces a small charge separation on the drop itself. The field pulls the drop's own mobile electrons slightly downwards, making the bottom of the drop slightly negative and leaving the top slightly positive. It becomes a tiny induced dipole.
Okay, so the drop is polarized just by falling through the existing field.
Precisely. Now remember, the air inside the cloud is full of ions, both positive and negative, created by collisions and cosmic rays. As this polarized drop falls, it encounters these ions. Here's the clever bit. Negative ions in the air are generally smaller and move faster than the positive ions, which tend to be larger molecules or attached to bigger clusters.
Okay, different speeds. How does that help?
The slightly negative bottom of the falling drop repels the fast-moving negative ions nearby, pushing them out of the way. But the slightly positive top of the drop attracts the slower-moving positive ions. Some of them might get captured as the drop falls past.
So it preferentially interacts with positive ions on the way down.
Initially, yes. But then, as the drop falls further, it enters regions perhaps already starting to accumulate negative charge. It collides with smaller cloud droplets, and there are complex interactions involving ice crystals, too. The overall effect, Wilson argued, is that the large falling drops, or ice particles, grapple, tend to acquire a net negative charge through these selective collisions and interactions. These negatively charged large particles fall towards the bottom of the cloud due to gravity. Meanwhile, the lighter, positively charged smaller ice crystals or ions are carried upwards by the strong updraft.
So the storm literally uses gravity and the updraft, combined with these microphysical charge interactions, to sort the charges. Negative goes down, positive goes up.
That's the essence of it. It physically separates charge on a massive scale, creating that huge voltage difference between the cloud base and the cloud top, and importantly, between the negative cloud base and the ground below.
And when that voltage gets too big for the air to withstand.
Then you get the discharge. Lightning. A single lightning strike can transfer a huge amount of charge, maybe 20 or 30 coulombs, from that negatively charged cloud base down to the Earth.
That's the recharging mechanism in action, firing the battery.
Exactly. It dumps that negative charge back onto the Earth, balancing out the continuous 1800 amp leakage current we talked about earlier.
Okay, let's visualize the lightning flash itself. You said it's not just one big spark. It's more complex.
Much more complex. It starts with what's called the step leader. The negative charge at the cloud base doesn't just leap to the ground, it feels its way down in jerky steps. Yeah, it sends out a feeler of ionized air, maybe 50 meters long, pauses for about 50 microseconds, then sends out another step from the tip of the previous one, often branching out, seeking the path of least resistance. It's this stepping, branching channel of negative charge moving downwards. It's relatively dim.
Like it's mapping out the route down, probing the air.
That's a good way to think about it.
Right.
It's creating a pre-ionized conductive pathway. Now, as this negative leader gets close to the ground, maybe within 100 meters or so, the electric field right above the ground becomes incredibly intense.
Because all that negative charge is getting really close.
Exactly. And the ground beneath it is relatively positive. This intense field literally rips electrons off air molecules near the ground and pulls positive charge upwards from the ground itself, especially from sharp objects like trees or buildings.
So positive charge starts rushing up to meet the descending negative leader.
Yes. A streamer of positive charge races upwards from the ground towards the tip of the step leader. When they connect, boom, that completes the circuit.
And that's the bright flash we see.
That's the return stroke. The connection opens up that highly conductive channel created by the leader, and there's a massive surge of current flowing up that channel from the ground back up to the cloud, neutralizing the charge along the path. This return stroke carries the huge current, maybe 20,000 amps or more, heats the air to incredible temperatures, like 30,000 degrees Celsius, causing the explosive expansion that we hear as thunder. That bright flash is the return stroke racing upwards.
Wow. So the flash we see is actually moving up, not down.
The main bright flash, yes, following the path paved by the downward moving step leader.
And often you see multiple flashes in the same spot, right?
That's right. Once that initial channel has been created, it remains partially ionized for a short time. So subsequent discharges from the cloud, called dart leaders, can travel down that same path much more quickly and smoothly, triggering further return strokes. That's why lightning often flickers.
And you mentioned sharp objects. That's why lightning tends to strike tall things.
Exactly. The electric field is always strongest near sharp points. So a tall tree, a church steeple, a skyscraper. The positive charge streamers are much more likely to initiate from those points, effectively reaching up and attracting the descending step leader towards them. They provide an easier path for the connection to happen. So let's kind of recap the whole journey here. We started with this surprising, quiet electric field, 100 volts per meter, right near the ground. That field exists because the whole atmosphere has this huge voltage difference, maintained against a constant global leakage current of about 1800 amps.
Right, the leaky capacitor idea.
And the batteries constantly recharging it are thunderstorms, hundreds of them globally, synchronized in their peak activity.
Inside, they use complex mechanisms, like Wilson's idea with polarized drops in ion speeds, driven by convection to separate positive and negative charges.
Which builds up enormous voltages, leading finally to lightning, that step leader feeling its way down, met by the incredibly bright, upward-moving return stroke that dumps negative charge back to Earth.
It's amazing. We went from just standing here feeling nothing to this intricate global electrical circuit powered by storms and culminating in lightning. It connects the ground we stand on to the highest reaches of the atmosphere.
It really does tie it all together. And maybe a final thought to leave people with, something Feynman's discussion implicitly raises. We mentioned that cosmic rays coming from outer space are crucial for ionizing the air, making it slightly conductive, which allows the whole circuit, both the leakage and the thunderstorm mechanisms, to work.
Yeah, the input from space.
So what if that input changed? What if solar activity or something else out there in the galaxy significantly increased or decreased the cosmic ray flux reaching Earth?
Hmm.
The conductivity of our atmosphere would change, the balance of that 1800 amp current, the effectiveness of thunderstorms, maybe even the frequency or intensity of lightning. It could all shift. The electrical state of our entire planet is subtly linked to the particle weather coming from deep space.
That's a fascinating point. A delicate balance maintained by forces both terrestrial and cosmic. Well, thank you for walking us through that electrifying journey, and thank you all for joining us on this deep dive.